Okay. So people at home, there is a vocab sheet linked into today's module, so I would recommend saving that. So, sorry. Back to your regularly scheduled programming. So in today's notes, we are going to be looking at some situations where you have a diagram that might have 4 triangles in it, and you need to use information from 2 of those triangles to show other information about another 2 of those triangles. So this says sometimes 2 triangles that you want to prove are congruent have common parts with 2 other triangles that you can easily prove are congruent. You may then be able to use corresponding parts of these other triangles to prove the original triangles are congruent. In other words, you might have to show one set of triangles is congruent in order to have information to show that a different set of triangles is congruent. So we're going to look at a proof of this. In this proof, we are given that angle 1 is congruent to angle 2, and that angle 5 is congruent to angle 6. We want to prove that segment AC is perpendicular to segment BD. Now, in order to show those are perpendicular, what are you going to need to have? Think backwards. What must you have to have perpendicular lines? Melissa? Right angles. Now, if you take a look at those, there might be a few different ways to show you have right angles. First of all, you can straight up show one of them's a right angle, right? Show it's 90 degrees. But also, won't 3 and 4 potentially both be right angles? And aren't they adjacent? So another way to do it, a slightly shorter way that you guys should kind of look for sometimes, is if you can show you have congruent adjacent angles, then won't you also have perpendicular lines? Yeah. And think about it that way, because if we have a bunch of little triangles, we might be able to show different parts are congruent. Because if you take a look, angles 3 and 4, isn't angle 3 in triangle BAO? And angle 4 is in triangle DAO? Those look like they could maybe be congruent, right? So if we can prove those are congruent, we can prove 3 and 4 are congruent. The thing is as of right now, do we have enough information to show these 2 triangles are congruent? No, we have that 1 is congruent to 2, that's a good start. We'll also have a shared side with AO, but there's really nothing else that you have. So we need to look at the bigger picture here. If you look at triangle ABC, that's that whole top half, and triangle ADC, that's that bottom half, we have a little bit more information, don't we? In that one, we have 1 and 2 are congruent on the left. We have 5 and 6 are congruent on the right. And don't you have a shared side all the way down the middle? So I can show that those top and bottom ones are congruent. Then I'll be able to show other little pieces in the picture are also congruent and maybe work our way towards those smaller parts. So let's start with our given. We're going to say that angle 1 is congruent to angle 2. And angle 5 is congruent to angle 6. That is given to us. We are trying to make our way down to that they're perpendicular. So we kind of talked our way through this. We need to show that the bigger parts are congruent in order to show the little parts are congruent. We already have our 2 sets of congruent angles. We now need to show we have a congruent side. Which side here is our congruent side for those 2 larger triangles? Maya? AC. And how could I write that in my proof? Good. Segment AC is congruent to segment AC. What property would that be? Very good. Reflexive property. Okay. Now I have enough information to say that that top triangle is congruent to that bottom triangle. So triangle ABC is congruent to triangle ADC. That is angle, side, angle. All right, now I need to now work on my smaller triangles here, right? We need to show 3 and 4 are congruent. I already have one little aspect of it. 1 is congruent to 2. But what else could I maybe say? What else do I have, Melissa? ABO is congruent to ADO. Oh, so you're thinking along maybe the angle side route. Yeah, we could do that. Sure, let's do that. Angle AB. Oh, wait, actually, we can't say that. I'm sorry. The reason we can't say that is because is angle ABO an angle in triangle ABC? No, it's split, right? With that line down the middle. If it wasn't split though, then that's an excellent idea. I like where you're thinking. We do want to show some congruent parts. If that one doesn't work, does anyone see maybe a side that we could show? AO is congruent to itself. Sure, let's say that. Segment AO is congruent to segment AO, again by the reflexive property. Okay, so we have this one. So we have a side and an angle. Reagan? With that one, so is BO a side in triangle ABC? Isn't it like a little side within it? So we can't quite do that. Is there a different side though, Ariana? AB and AD, yeah, because that's an actual side of your full triangle. BO is like an internal side, so we can't say that one yet. Oh, sorry. So we want to say that side AB is congruent to side AD. Now, what allows us to say that? Didn't we say the full triangles are congruent? So are their parts congruent? That was CPCTC. Good. So now I have the triangle AB. Now can I say the triangle ABO is congruent to triangle ADO? Yeah, we have a set of congruent sides, an angle, another set of sides. So we're going to say triangle ABO is congruent to triangle ADO by side, angle, side. Now, what can I say about angles 3 and 4? If I know the full triangles are congruent, what can I say about 3 and 4, Anne-Marie? Yeah, we'll say they're congruent by CPCTC. So angle 3 is congruent to angle 4 by CPCTC. If 3 is congruent to 4, don't we have congruent adjacent angles? Which technically means they're 90, right? Which implies that we'll have perpendicular lines. That's our perpendicular lines theorem. Congruent adjacent angles make perpendicular lines. So then we can say that segment AC is perpendicular to segment BD. That is the perpendicular lines theorem. Or you can write out the statement, if you have congruent adjacent angles, then the lines are perpendicular. Good. No, because we're concluding that lines are perpendicular. So we had congruent adjacent angles, and that implies that the lines are perpendicular. It doesn't really matter with this part. That more depends with like the angle theorems. Reagan? There's a short portion of always, sometimes, never. Yeah. Yes, Emery. Yes. Okay, so you guys are going to be happy about this part. The following chapters will often have you outline your proofs with just the key steps. So there is now going to be a few different types of ways to present your proofs. First of all, we can still have our traditional 2-column proofs. Those are still going to occur, which need to be nice and detailed. But sometimes you're just going to be asked for key steps. And key steps, well, let's take a look. We have a proof to look at. Let's figure out what our key steps might be. What are some things that maybe stick out to you guys as things that would definitely be essential? Or we can even work backwards. What do you think might not be as important? Reagan? Oh, yes, Riley? I would say so, for sure. Reflexive property, can't we kind of assume that things equal themselves? Yeah, in our two-column proof, we really need to say it. But if we're just talking about the essentials, reflexive property is not an essential. I would say a property that is essential is like substitution. If you're taking things and plugging them in for something else, that you can't really imply as much. But if you have like the reflexive property, that could be implied. If you had an equation and you needed to subtract something from both sides, that could be implied because you can see it's equal on either side. Reagan? The given, actually, no. I would say the given, you're already told it. It's already stated at some point. It doesn't have to be restated. Melissa? I would say CPCTC is essential. CPCTC is definitely essential. That really connects like different parts of triangles, right? So I would say all of your CPCT steps are essential. To save us some time, I'm going to highlight them. If you want to write them below, you may, but I'm going to highlight. Okay, so I would say these are essential. What else do you think is probably essential? Steps 3 and 6. I agree. Those are the, when you're saying the triangles are congruent, right? You gotta say your triangles are congruent. That is essential. I see one other essential thing. Come on, guys. What's essential? What are you trying to get to? Maya? The actual proof, right? Where you're trying to end up is definitely essential. If you don't say that, you haven't finished the problem, right? So I would say these steps are essential. If I asked for your key items, these are them. Given, throw it out. You already know it. Reflexive property, we can apply it. Those are the main things that really happen in this chapter that are non-essential, but it kind of helps shorten things up a little bit. If you wanted to, you could rewrite these down here. I'm just going to say, hey, anything that's highlighted, that is definitely essential. So I would say there's some properties we could throw out. Something else you're going to start to see are paragraph proofs. Paragraph proofs are written in sentence form rather than two-column form. They often tend to focus on key steps, or else you're going to have like huge paragraphs. And then the main difference between paragraph proofs and two-column proofs is the word because, right? Triangle X is congruent to triangle Y because of the side postulate, right? That's that key word there, which is implied with the two columns. So I'm just going to quickly kind of turn the proof above into a two-column proof. There is more than one good way to write it. I'm just going to kind of show you one example, okay? So what I would maybe say is we don't need to write our given, but we did start with the two triangles being congruent, right? So that's where I'm going to start as well. We can say, where did I put my written thing? I had it written out really nicely and some like, with some great grammar going on. And then I put it. Oh, here it is. Okay. So we are going to say that triangle ABC is congruent to triangle ADC by the angle side angle postulate. And I still don't mind some abbreviation in this. So that's where I would start. You don't need to state your given. We're going to start here. Then, didn't we find some corresponding parts? And that implied some more things were congruent. So that's where I would go from there. And again, your connecting words that you choose, how you choose to phrase this can vary. I'm just going to say, therefore, corresponding parts segment AB and segment AD are congruent, right? We knew that because of our angle side angle. Since segment AB and segment AD are also corresponding parts, in triangle ABO and triangle ADO, they are congruent by SAS. Okay, so since segment AB and AD are also corresponding parts in triangles ABO and ADO, they're congruent by side angle side. So corresponding parts, angles 3 is congruent to 4, and segment AD would therefore have to be congruent to segment BD. Again, when you're writing this independently, there's 1,000 different ways to write it, right? And your order doesn't even have to be exactly the same because maybe you said certain things before others. You could even simplify it and say, since AB is congruent to AD, then triangle ABO is congruent to triangle ADO because they're also in that triangle, right? There's a lot of different ways to phrase it. This is just one example. All right, so real quickly, I want to just try out one that we're looking for key steps in. Give the reason for each key step in the proof below. We are trying to prove that angle 3 is congruent to 4. So the first step here, they concluded that triangle LOB was congruent to triangle JOB. How do you think they determined that? Triangle LOB is congruent to triangle JOB. Maya? So for this one, do we have any, well, we have that angle 3 and 4 are congruent, but do we know that any of the triangles within LOB and JOB are congruent? No, but what do we have? It doesn't need to be stated because it's a non-essential step. Reagan? We don't know that any of the angles in triangle LOB and JOB are congruent. They're not marked for us. Peyton? How'd you get side, 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 Peyton? Right, we're already given 2 sets, and then we don't need to say it because it can be implied, but don't we also have a shared side in the middle there? Yeah, so this would be side, side, side. Again, you might need to mark it for yourself. It just doesn't need to be stated. What then allows us to imply that angle 1 is congruent to 2? Melissa? Yep, CPCTC. Those are corresponding parts of congruent triangles. Okay, so now I know that angles 1 and 2 are congruent. How can I then imply that angle LBA is congruent to JBA? What do we think? We have that angles 1 and 2 are congruent, 3 and 4 are congruent. Think about what else you would have to know, and then what theorem that would be. Melissa? Side angle side. Where are side angle side? Do we have 2 sets of sides in angle LBA and JBO? Angle side angle. Good. What's the side though, Melissa? That reflexive property again, right? That's why that's non-essential. BA would be congruent to BA. So we can say then angle side angle. And then if we know that, what then allows us, or I'm sorry, wait, I wrote something bad here. I did a bad thing. We do not know this. My bad, Melissa. You were right the first time. We know that triangle LBA is congruent to JBA because we have your set of congruent sides here with BA, and then we had LB and JB, and then angles 1 and 2, so it was side angle side. I was looking at 3 and 4 as already knowing they were congruent. That's where we're trying to get to. I misread that. You were right the first time. It's side angle side. Is that what you were going to tell me, Reagan? Yeah. Yeah, side angle side. Yeah, I misread it. Good. And now we know 3 and 4 are congruent again by CPCTC. Good. Okay. So this next part, we're going to have to abridge a few things. Let's see what we got here. If we do not get to the always, sometimes, nevers, they are filled in on the module. Okay, so I would recommend trying them out and then you can go back and check them. But I at least want to make sure we hit on our vocab so we know what everything means. A median. A median is a segment from a vertex to the midpoint of the opposite side. This is from 4.7. 4.7 deals with special segments and triangles, medians, altitudes, and perpendicular bisectors. Something important to mention is, so any of these segments can be drawn from any side in your triangle. So a median is a segment from a vertex to a midpoint. So for example, you could draw a median from A to the opposite side here, and it's going to split your triangle, that bottom side, into two congruent parts. But you could do the same thing going from from vertex B to the opposite side, or from vertex C to the opposite side. So each of these could contain 3 medians, 3 altitudes, or 3 perpendicular bisectors. An altitude is a perpendicular segment. That's very important. It is a perpendicular segment from a vertex to the line that contains the opposite side. When you see altitudes, think almost like height. Okay, it doesn't have to go from bottom to top, but it's that kind of a measurement. This can look a few different ways. In an acute triangle, all 3 altitudes are going to fall inside your triangle because they would come from the vertex to the opposite side. That's just one example. You could do the same thing from vertex B or from vertex C. In a right triangle, 2 of the altitudes are actually the legs, because think about if you tried to draw an altitude from D, wouldn't it just hit vertex F? Wouldn't it be perpendicular right there? That's technically the altitude, okay? But you could also draw it from F to the opposite side, and it would look something more like this. Okay, so just keep that in mind. And then if it's an obtuse triangle, 2 of the altitudes are going to fall outside of your shape. Because if I try to draw a segment straight down from G, then what's going to happen here is it's going to intersect right there, right? You're gonna have to draw an auxiliary line and kind of extend that down, okay? Yes, Anne-Marie. Yes, you could also go from point I to the opposite side, and that one would be the one that falls inside. Yeah. And there's a bunch of diagrams on these. If you look in your textbook, they have each one drawn out for you, so you can check that out. A perpendicular bisector is a line that is perpendicular to a segment at its midpoint. It's like you're combining those 2 vocab words, perpendicular and bisector. You're going to have a segment. A perpendicular bisector could be a line, a segment, a ray, pretty much anything that goes through the middle and forms a right angle with it. And then the distance from a point to a line or a plane, the length of the perpendicular segment from the point to the line or the plane. So what this is saying is if I ask you what is the distance from a point to a line, it's basically saying that it is always the perpendicular measurement. The shortest distance between 2 things is always going to be perpendicular. Don't you always want to kind of try to draw a segment directly to it? The shortest distance is always perpendicular. And then we just have some theorems. They're very similar. The perpendicular bisector theorem says, and this top picture is an example of a perpendicular bisector. Segment AX is bisecting segment BC, and it is also perpendicular to it. So that's what this diagram is of. If a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. What that means is any point on this bisector is going to be the same distance as it is from B to C. So like, for example, point A is going to be the same distance from B as it is from C. So the measure of AB would have to equal the measure of AC. Equidistant literally means equal distance. And then vice versa. If you already know that a point is equidistant from either endpoint, then it must lie on the perpendicular bisector, right? If it's the same distance from the left and the right, it has to be falling on that bisector. Does that kind of make sense, guys? Okay, and then angle bisector, exact same idea here. If a point lies on the bisector of an angle, then the point is equidistant from the sides of the angle. So in this picture, point P is lying on your perpendicular, or is lying on your angle bisector, right? We can see we have an angle bisector here because of the congruent angles, and what this is implying is that the measure from P to X is going to be the same as from P to Y. So P to X would equal P to Y, and it'd be the same thing from Z. And then one last thing, if a point is equidistant from the sides, then it lies on the bisector. So just the other way around. If you know it's equidistant, then it's on the bisector. Okay?